Now in this tutorial we will learn how to run your simulation in Fluent. First we will import our mesh into the Fluent and set parameters. So first go and open Fluent. Set your directory to the folder where you is your mesh or wherever you want. Desktop, square cylinder. Okay. So first we will import our mesh. So go to the file, read mesh, and go to the folder where your .msh mesh is residing. So just double click on it. Yes. Your mesh has been read. Go to the display, display mesh, display. Now you can see your mesh and you can pan you using your left mouse button, and you can zoom in, zoom out using a scroll button, right? So first we will check mesh properties, check. So the x coordinate is -20 and +20. So this is a 40 by 40 mesh and the minimum volume is 1.0 10 to the power -6. So the minimum volume must not be negative. Another statistics are given here. When I also check the quality. So the orthogonal quality is from 0 to 1 where 1 correspond to the high quality. So the minimum orthogonal quality is 1 because this is the Cartesian geometry and the aspect ratio is 3.8 raised to the power 10 3. Also you can check size. So the number of cells are 7488, number of faces 15,168 and nodes are 7680. So now we will define the properties and parameters. So first go to the solution setup, go to the general. So if it is a study flow, choose a study, and if it is a unsteady flow, choose transient. Here I will choose transient, and type is pressure based. If the flow is incompressible, choose pressure based. Otherwise, for the compressible flow, choose density based. Velocity formulation absolute, 2D space is planar. Now model. So if you want to run laminar flow or inviscid flow or turbulent flow, these are the turbulent models. This is the laminar. So choose this. And if the energy is also concerned, you are concerned with temperature, then you should on this energy equation. But we are simply showing incompressible flow over a square cylinder. So now go to the materials, choose fluid as air. Now we will set here our properties. So put density 1 and viscosity as 0.01 for because we are going to run this simulation for Reynolds 100. Our characteristic length of the square cylinder is 1 and the velocity we will give 1. So the round number will only depend on viscosity. So if you want to Reynolds number 100, choose this viscosity as 0.01. So do not forget to change or create. Now close this. Default cell zone conditions default. Now boundary conditions. So at the cylinder, uh, boundary will be boundary condition will be wall type. So the cylinder walls are not moving. Choose stationary and shear condition is no slip. Similarly at the inlet, At the inlet we have to provide velocity, so it's a uniform velocity coming from left to right of one magnitude, and at the outlet the flow will exit at atmospheric conditions, so the gauge pressure will be zero, and the symmetry is just symmetry, leave it default. No dynamic mesh, ref- reference value compute from inlet. Now the solution method, there are the many schemes, strategy to solve the fluid flow, to solve the Navier-Stokes equation. So choose simple, and first choose the standard and momentum first order, and now solution control, leave it default, monitor. So go to the residual, double click, and set this to 10 to the power minus 6. So residuals are errors which should decrease, and whenever it falls to the 10 to the power minus 6, the iterations will be converged. Now you can also measure lift and drag, create drag, select cylinder wall, print to console, plot, write it in a file. The file name will be cd history and will be stored in your folder, this folder, and select x direction 1 because the drag will be acting in the x direction. Okay, again create coefficient of lift, select cylinder wall, print, plot, write. So the force vector direction will be y because the lift will be act in y direction. Okay, now solution initialization. So typically we select initialization from inlet. So the velocity has changed its value from 0 to 1. Now initialize, click here, it is a must. So the solution has initialized. Now calculation activities, go to the edit command. So we will save our data file at every, suppose 10 step, and we will save the associated case file. The case file is where all these parameters which we are given is saved. So the your data file will be saved in this location. You can save wherever you want. We will right now we'll save it in square cylinder folder. So you can change the file name. The file name should come up with flow time or time step. So let us time step. Okay, now run calculation. So the time step size is suppose 0.01, and maximum iteration per time step is suppose 500. Now click calculate. So the residuals are dropping. The solution will be deemed to converge if all the residuals will reach to 10 to the power minus 6, right? So this is the quantity equations residuals, and this is the x and y velocity residuals. All the residuals had dropped to the 10 to the power minus 6, which we have set for the convergence criteria. Otherwise, the maximum iteration will be 500, which we have set here. So again, if you want to go to 10 second, we have to go increase the number of step size to 100,000, and now calculate. So after each time step of 10, your data file will be saved here in a square cylinder. So your drag and lift and conversion history is plotted. This is the coefficient of lift is being plotted. Similarly, drag data is being plotted, and the scaled residuals, right? So it will take some time to reach the, so So you can see now that the case file and data file has been generated in your folder, and after each time step similar files will be created here. So cancel it and it will stop at the end of the iteration. So now we will increase the accuracy order. Go to the solution method and go to the momentum second order and run calculation again. And you can also see that CD and CL data are being stored in a file. So in the next part we will show how to plot our contours of pressure and how to plot streamlines. So for this we can go to the graphics and animations and can produce contours and etc. In the next lecture we will do.